So in this lesson, we've been talking about finding volumes by slicing. And some of the examples we went through, we had a function that either rotated around the x-axis or rotated around the y-axis, and then it created a solid. And then if we started taking cross sections of that, we would get either a disk if the volume was solid, or we would get a washer if there was some kind of cavity within that shape so that it creates a hole in the cross section. There are times where you can find the volume without having to rotate. It has a square base, but the cross sections are triangle. Then we would have something that looks like this. Trying really hard to make this look three-dimensional so you can see what's going on here. Okay, so this is our picture of the solid. So the base is square, but when I go to take a cross section and I slice it, my cross section is going to be a triangle. And no matter where I slice it, it's going to be a triangle. Now, if this was on a graph, if the base was sitting on a graph, and this was the point 0, 0, and this was the point 5, 0, then what we would want to do is we would want to integrate from 0 to 5, because this is the interval that we're interested in. And we would want to integrate that area of the triangle over the interval from 0 to 5, and that would give us the volume of this object. So just like when we did Riemann sums, and we were trying to find the area between a curve and the x-axis, we would make rectangles, and we would add them up to add up the areas of the rectangles to approximate the area between the curve and the x-axis. And then the more rectangles we made, the more accurate the area was. So if you imagine that you keep adding in all these slices and you do it so that you jam in as many as you can from here to here, that's all the areas added up. And that will give you your volume. So we're going to do the same idea here, it's just that it's kind of an irregular shape. So in this example, we have three functions. We'll call the blue function b of x. We'll call the red function r of x. And we have this green line that's at x equals 1. Now, if we had cross sections that were square, if you can imagine, when we lay all these squares down, I'm trying to show you this, but it's not working out so good. So imagine you have this square. This edge of the square, imagine that you're going to glue it right here, and this is going to get flipped up so it pops out of the page and makes it three-dimensional. So these are going to be our cross sections, and this is going to be our base where all the equations create this bounded region. So we need to find the area of each of those squares and then integrate it on the interval of interest. So our interval of interest is going to be from wherever this intersection point is to x equals 1. Now we're doing this with respect to x because the question says that our cross sections are perpendicular to the x-axis. If we were doing it the other way, where it was parallel to the x-axis or perpendicular to the y-axis, then we would want to look at it in terms of doing this with respect to y. So we want to find the area of the cross section, the area of the square, and integrate that. Let's say this point right here at the intersection is, let's say, I don't know, negative 0.1, and let's say, I don't know, 0.5. It's off the x-axis, but just barely. So if we're going to integrate this, we're going to go from negative 0.1 and then up to 1, because we're doing it over this interval. Now the area of the square, because it's a square, both the length and the width is going to be the same. So I could just find the length or the width and square it, and I would get the area. So if I find the length of the square, I can do that by finding the difference between the bx and the rx. This is going to be the edge of one of my squares, so the length is going to be the function b of x minus r of x. So my area of each of those cross sections is going to be b of x minus r of x, and square it. So this will give us the area of the solid where the squares pop out of the page and create this three-dimensional shape, where this is the base that would be sitting either like on the ground or on the table, and then the squares would pop out of that base.